I guess, a little advanced presentation here on foreign function memory API. So in this particular presentation, we're going to talk about what it is, first of all, and what about JNI. I accidentally deleted that slide, I just realized, but we'll talk about it. Memory segments and arenas, linkers, up calls, down calls, how to deal with pointers, and JExtract. So if you've been to a presentation of mine, I go about it the hard way. Like I was just thinking about it. All my presentations have like code and slides and code that you could take and use. And if you want to try out the code, great. And if you want to submit something back, that's great as well. So all slides, there's a PDF in there for the slide, and you can go here to this particular URL. That's the same as the QR code that you see up here. So I'll give it a few seconds there if you want to take a snapshot of that. In 10, 9, 8, 7, 6, 4, 3, 2, 1. All right, here we go. All right, excellent. So foreign function memory API, really? It just allows us to connect to C programs, the underlying C programs, and uses something called an ABI, which allows us to connect to those native libraries. And we could process the native data without the brittleness or the danger of JNI. So things like overrunning memory, things like calling things that do or don't exist. There's a lot of safety now with the FFM or the foreign function memory API that JNI did not have. So we're going to show you how that works. Particularly the memory. So one of the things that we're going to be doing in this presentation is talking about something called arenas. And arenas are going to be that memory space that you can use. Things are confined, things are safe as you tend to use the memory. The API allows us to invoke foreign functions, code outside the JVM, safely access the foreign memory, and memory not managed by the JVM. So we have arenas, we have segments, we could set up that memory. And once we set that up, we can call C libraries. Let me just make this point over here. I was in a unconference a few weeks ago. I was talking with someone who is already using the memory segments, but not really using the foreign function stuff, but just the memory. And that's what they're all about. So if you want to, you could do so. And just talk to someone who did that. And I thought that was an interesting point. They just wanted to set things up in memory, store things in memory, and then just take it back. Solid, you could do that. But you can set things up in memory and then call the C libraries to handle that. You can send pointers to methods, or you can receive a pointer from a C method. You have memory layout, structured access, so you can create structs for that. You check native errors. You could slice memory into components. We'll talk about restricted methods. All these are going to be a part of what's called a restricted method. And so you'll need to add a switch to your Java runtime in order to run those, and JExtract. And we'll talk about JExtract. So who's going to use this? The developers who are going to want to do something with off-heap memory is going to be the developers that, or are going to be the developers that are going to be really interested in this. I think people who want to create machine learning models and make calls in C could do so. You can make calls to Python, right? So if there are libraries that you wish to use and you want to tie into the backend C for some of your favorite things, then you could do so. And I think it's really wide-ranging for all the different things that you can use. Image processing, and one of the things that I was hoping to do before arriving today, but I have that done, and that's fine. I have a lot of examples, so no problem there. But I've always wanted to get a scanner and write my own application that would scan documents from my Fujitsu scanner, and that has a C library, and I just want to tap into that. So I think that's totally possible for me to do. And again, you can just think of many things that you want to use. There are a lot of C libraries out there. You want to make system calls. You want to do cryptography, audio processing, device interactivity, and more and more. If there's a C library that you wish to use, you could use it. One of the examples I'm going to show at the end here is I have a Rust application, and that Rust application, I could make it externalized so that way I could tap into it. Wonderful. So lots of different things that you can do. Foreign function would typically not be a concern. This is a strong opinion on my part. If you're an application developer and that's your job, you write a Spring app, you'll probably never see this and probably never use this, okay? So goals of the foreign function memory interface, be productive with it, replace the brittle machinery of JNI, which was the older version of that, with a concise, readable, pure Java API. Performance, so provide access to foreign function memory with overhead comparable to, or even better than, JNI, Java Native Interface, or Sun Miscellaneous Unsafe. And you've probably been seeing some of these warnings depending on the library that you use, right? Hey, you're using Sun Miscellaneous Unsafe or there. Platform support, uniformity, provide ways for structured and unstructured data, soundness, integrity, all the good buzzwords along with it. So in other words, make native call and make it safe for you to use. That's the idea. So off-heap memory. So the Java memory model looks something like this. Whenever we run a particular program, things get placed on the stack, and these would be things like primitives and references to objects. But objects are not going to be stored on the stack. They're going to be stored on the heap. So when we say off heap, it's not here. So again, the thread stack, primitives, references are what gets placed on that particular stack. So primitive, but object references are going to be placed here on the thread stack. But what do they point to? They point to the section in memory. So these are where the objects are going to be. Okay. Now off heap is, let's not put this on the JVM. Let's put that on the operating system. Okay. And so in this case here, we're going to be using an arena. We'll talk about that. But the idea for an arena here is that this is going to procure memory off heap, which will be on your operating system, okay? And that's the idea of what off heap is. There are a lot of things that use off heap. So one of the things I do as part of my day job is I do a lot of Kafka, and Kafka uses something like page cache, right? And that's something that is native that they use. That's a section of memory that is part of the operating system. And for those that use Kafka, one of the things that makes it fast is that when a message comes in, it gets placed on that page cache, so that way it's readily available for consumers. And one of the things that they wanted to avoid was the garbage collector. The garbage collector can sometimes, take up some pauses, and those pauses can affect the speed of your application. So there are many applications that would rather just store that memory onto that operating system, and that's what we mean by off heap. Okay, so yeah, garbage collection. They're stored in heap. Garbage collection is amazing, and it keeps getting better. And we have lots of different kinds of garbage collections out there. But for performance-critical libraries or applications or frameworks, that could be too costly. So if it is, that's what this is for. Okay. So again, how can we do it now? We have byte buffer. We have Sun Miscellaneous Unsafe. Byte buffer directly stores information onto these byte buffers, which are backed up by off-heap memory. But the thing is that you're limited to 2 gigabytes. So one of the things about the foreign function memory is that you're able to store memory. Okay. And then this right here is deallocated only when the buffer object is garbage collected, which developers cannot control. So one of the things that you get with FFM is the ability to create arenas and decide at which time does that get recollected. Okay. Here's this one here, but this one is Sun Miscellaneous Unsafe. Low-level access to on-heap memory. It also works for off-heap memory. It's fast, has huge regions for that, can be called at any time, but the programming model is weak because it gives developers too much control. Okay, and that was one of the things that they wanted to tie off a little bit better. Okay, so long-running application can allocate and interact with multiple regions of off-heap memory over time, and data in one region can point to data in another region, and they must be delocated in the correct order, or else dangling pointers will cause some of these use after they have been freed bugs. Okay, so with this FFM API, we can allocate, we can share off heap memory and have predictable deallocation. So that's what this is for. So that way we don't have to use that unsafe. Okay. Now, when we interact with things, we have abstractions. So a couple of the abstractions that we'll be using are like method handles and variable handles. So if I put something into memory, I can use a variable handle to reference it. I could also make method handles, which are going to be methods in C that I can refer to. And that's what that's all about. Okay. Simplifies writing, building, distributing Java libraries, and capable of modeling foreign functions, native code, and off-heap data for whatever it is that you need. So some of the things that we're going to be using in these demos that I'm going to show you is allocating and deallocating memory. We have things like memory segment arena, segment allocator. This will allow us to manage memory. We can use memory layout, var handle. This will describe the data and kind of provide us a schema. That's what that's all about. Provide some sort of structure for that. And then once we have that, we can call foreign functions using linker. We'll talk about that. Symbol lookup, which means, hey, I need to find a function on a particular library like an SO or a dylib function descriptor, which describes the function, and method handles. Okay, so those are the interfaces that you are going to be using for this. Everything is going to be stored in the package. Where is it? In the package. There it is, right down there. Java lang for it. Okay, so that's going to be the package that we're going to be using. It's already been released, part of Project Panama. So Project Panama has foreign function memory API, JExtract, which I'll show you. Vector API is also a part of that, but that's still in incubator. That's still on the 8th incubator, which is waiting for stuff from Valhalla. Okay, but it's an official now, and it has been released with the JDK 22 delivery. Okay, all right. So one of the things that we're going to deal with when it comes to memory is spatial versus temporal. And you may hear these terms. What does that mean? Spatial means a segment determined by the range of memory addresses that you wish to use. Temporal is going to be the lifetime. How long do you want to keep it? And the reason I bring this up is that these words are going to be coming up a lot. So if you decide to use this particular API, it'll say this is spatial or this is temporal. All that means is spatial is how much space do I want? Temporal is how long do I want to keep it there? Okay, and that's what's meant by those particular bounds. So we have arenas. And so what's an arena? An arena is very much like this, right? Everything is going to be self-contained in here. And, I think you've been to the Coliseum before. So this would be essentially your playground, the one that you use, okay? And that's the idea for an arena. So arenas control the life cycle. Each arena has scope, which specifies the region of memory that you want to use, and can be accessed if the scope associated with it is still alive or not. And you get 4 different kinds of arenas. So again, this is just setting up off-heap memory on your underlying OS. And so what we'll have here is we'll have confined, we'll have shared, which means obviously you could share that memory with others, automatic, which will create the memory for you, but it'll be up to Java to go ahead and turn that down, and global, which means this is for everyone and it's going to be global. But let's go ahead and break it down. All right, so as we do this, confined, created with arena of confined, you put this in a try-catch block or a try with resources block, bounded and deterministic lifetime, because once you close it, then that's done, okay? Confined area has an owner thread, so that's going to be the other thing on whether it's shared or not, another important point here. And only the owner thread can access its memory segments. You'll get an exception if you try to close the confined area with a thread other than the owner thread. Okay, that's an easy one to use. Shared arena has no owner thread. Multiple threads can access this memory, and any thread may close this shared arena. Kind of see the different characteristics here, right? So automatic is arena of auto. You do not put this in a try with resources block. That's going to be the important thing here. Area that's managed automatically and by the garbage collector, okay? And if you call arena close on an automatic arena, you'll get an unsupported operation exception, okay? Because it does that for you automatically. All right, global arena is any thread can access this memory allocated with this arena. And in addition, the region of memory of these segments is never deallocated, so it's there forever. So if you close a global arena, you'll get an unsupported operation exception. So which one do you want to use? You have different choices that you can use, okay? Confined is easier, I think, to work with for samples, but you have a lot of these in case you want to set up some memory. So again, this one is going to be as far as the temporal bounds, program lifetime. All of these have whatever space that you wish to use. Automatic will close on GC. Confined will be manual. You decide when to do that, which means you could put that in a try with resources, and shared will be manual. Okay? Cool. All right. So we have that. Now let's bring in the linkers. All right. So what are the linkers? Native linker provides access to libraries that adhere to calling conventions of the platform in which the Java runtime is running. These are called native libraries. What? That sounds technical. What the heck does that mean? Well, that means that this linker will allow us to link to some library. That's it, right? And that's what the linker is going to be. Okay. So locating the address of that C function, to call it, you will make a downcall method, which is a method handle. So you get this reference back called method handle that points to the native function. So once you have this, you can call whatever native function you want on the underlying OS, okay? This instance requires the native function's address. To obtain this address, you'll do something called a symbol lookup, okay? And once you have that, you can make that downcall button and start to use it that way. So I'm going to be using terms called upcalls and downcalls. What is that? Well, let's take a look here. A downcall is going to be from Java to C, okay? The upcall is going to be, did I do this one right? No, I didn't. All right, here, really quick here. La, 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 la. Let's pretend that never happened. And one more. And there we go. There we go. Nothing ever happened. Yay. All right. So there we go. And it's like I never made a mistake whatsoever. All right. There we go. So upcall is going to be C up over to Java, which means I could give it a stub like a function, and then that C, underlying C, can give a call over to Java. That's the idea there. All right. So function descriptors. Let's take a look at that, and then we'll bring it all together. So function descriptor describes the native function that we want to use. That maps C types to something called value layouts. We'll see how that looks. The value layouts are used by the linker to create a method handle, okay? So I threw a lot of stuff at you, but what we're going to do is we're going to make a simple call here for a C library. So first thing that we're going to do is we're going to create a native linker. Next, we're going to find the address of that C function that we want to use. Then describe the function signature, right? This is the structured part. This is essentially the schema of the function that we wish to use. You would have to provide that in Java. Then create the down call handle to that particular C function, and then call the C function directly from Java, okay? All right, well, let's kick it into high gear with a demo. Here we go. So I threw a lot of stuff at you, and what I'm going to be doing is I'm going to be using C. How many of you still program in C? Just out of curiosity. Okay, 1. All right, you tell me if I did it wrong. All right, so what I have here is I have some C code here. Let's start here with add ints. That's going to be an easy one. So I have int add ints right over here where I'm bringing in an int A and int B. And I'm going to be using a multiply double. We'll talk about struct a little bit later on, but I'm going to just focus on these two right now, right? One, I have two ints. The other one, I have two doubles, and they're either returning a int or a double from here. So in order to build this, what I did here is the following. So if I'm on a Mac, so I'll be using GCC shared. Make sure that I have the shared on this one. And what I'm going to do is I'm going to output this one into a dynamic library since I'm on a Mac. Right over here, this will be the Linux version, which will be a shared object. And then on Windows, a dynamic link library. Okay. So I'm using GCC here to compile that particular code. And as I do so, I've already done this here for this particular session here, libffm kata dy lib. Okay, so there's the dynamic library that I wish to use. Okay, so far so good. Now, how do I call that? Well, I'm going to come over here to Java, and I'm going to open up this kata test here. And what we're going to do is the following in here. And let me go ahead and expand this. So my goal for this, I don't know if it's quite ready yet. I know it works on Mac, and I haven't tried it on Windows or anything else. But I try to set this up so that way you can use whatever OS name if you decide to use it. And then the other thing here is I wanted to keep those katas really small, so that way it's easier to comprehend on here. I think one of the things about the documentation for the FFM on the website is that it's really verbose. And I like these katas here because they're really lightweight and you get to see the point right away. So that's what I have here. And here's the add ints. Let's take a look at that one. And I'll expand on this one. Right? That one was just adding two ints on C. So all I'm doing here is I'm calling arena of confine, which will set up an arena that I could use memory on. And here's the linker. What is the linker? Let's come over here. Linker, native linker, which says go to the operating system, okay? Because I want to look for stuff. And weird. Where did we go? All right, yeah, let's come back over here. Okay, so that's the linker. This says down call handle, which is I want to make a call to the C library, and that's where this is. Now, on this lookup, I have a method here called lookup that I just created here. And this one's the lib path. And this one right here is going to be the location of that path. So I have this just little utility here. And this one just says, I want to use lib ffm kata dy lib for the dynamic library. Okay? So coming back over here, maybe. There it is. Yeah, here's the add-ins right over here. So I just created this lookup here so that way I could just find out where that library is. That's what that part is. Then what I have here is I have find add ints, which is the method on C. Otherwise, throw that. Okay? So that's linking to the C function. Next, right over here is the structure on this. And what this one is function descriptor of Java int, which is going to be the return type. This Java int is going to be parameter 1, and this Java int is going to be parameter number 2. Okay? Now that I have this will return a method handle. Method handle is just going to be the handle that you'll get to interact with your C library. And once you have that, you will have a invoke. Invoke is very flexible. There's another one that's called invoke exact, which is going to force you to use the correct types. So this one's a little bit more flexible, and it's called invoke. And once you have that, you can get the result. So if I run this, and it did work before, there it is. Now, one of the things you'll see over here is this, restricted foreign symbol lookup. It is just a warning, but this warning is going to say use something called -- enable native access because this is just a warning. Because they want you to explicitly acknowledge that this can potentially be unsafe. And so therefore, because I'm doing this, library lookup is what they call a restricted method. And so if I want to run this, then I would have -- enable access here. But that worked. That was pretty cool, right? So yeah, let's take a look at the C code again. This one's multiply double. Let's see what that one looks like. Here's the multiply double. Same thing again. Establish your arena. Once you have your linker, do a down call handle. Look up your library. Find the method within that library and provide the function descriptor. Now, I'm going to tell you about JExtract a little bit later, but JExtract, its job is to look for the schema or the structure of it, and it will do that for you automatically. Okay? So what I'll do here is I'll do an invoke and do the result, and I'll have a delta for this, and there we go. That's calling my C library, and that's how that works. Okay? So pretty cool. So memory segments. So those were easy because those were just primitives, and I could just say, hey, here are the primitives. I just want you to use those. So memory segment represents a contiguous region of memory. So let's say I want to call a C function, and I need to set up some memory, and then I need to tell that C function, here's the memory. I'm pointing to it. You call it from there. Okay. So native memory is how we're going to be using that. Allocated through an arena, so you'll do arena dot something and allocate it this way. And various ways to get segments, again, you'll be using the term allocate for that one. Finding native libraries, again, we have the native linker, the default lookup. But the thing I wanted to mention here, for this next demo, I'm going to use default lookup. Default lookup will go to the C libraries that comes automatically with your operating system. The previous two that I just did were just going to a particular library, particular DY lib, or a particular SO, or a particular DLL. This one's going to your operating system, so it'll find all the utilities within your operating system. So if you want to use qsort or stringlen or free or malloc or anything that comes with your standard C, then you'll use linker default lookup. That's where that comes in. All right. So let's take a look at this one. Well, on this one's coming from the Oracle one. I just took that one because it was easier and had everything I had. I made some little bit of changes to it, but let's take a look at this one. So what's going on here? All right. I think you got it now. We have area of confine. So this is where I'm going to create the arena, the space for my memory. And then after this gets closed, then there goes that memory. So that's going to make that safe. And then I have an arena allocate from. Now, the thing about this is if we take a look at the allocate, you see all these different ones from double to addresses. And these value layouts will allow you to craft whatever kind of types that you would like. And we'll be using that with a struct. So that's the allocate from. And what this one's going to do is it's going to allocate a string on off-heap memory. And once I have this now, this will have a memory segment associated with it, which this is going to represent the memory, right? The memory in the JVM, but it's pointing to the memory off heap, okay? Now, because of this, take a look here. I am using default lookup, and this is going to allow me to look for functions on my operating system like stringlen, okay? That too is a memory segment as well. Now, stringlen, here it is. Stringlen is going to take an address. And remember, the return type is always going to be the first one. And that will return a Java long. So down call handle, which this part's kind of interesting, because here's the address for that. And then here's the function descriptor for that. Okay? I'll get a method handle for this. And here it is. Now I get to invoke that. And we are good to go. Kind of a nice, simple API, right? So all this is set up the memory and then tell the remote call, there's the memory. It's already off heap. It's already in your neighborhood. You just go ahead and call that, and we are done. Okay? Not too bad, right? So, excellent. Structs. So in C, there are structures associated with it. So For something like that, you can use memory layout, struct layout to construct C structs in Java. You allocate and access struct memory. Everyone knows what a struct is, right? Struct, and you have the fields associated with it. Since C doesn't have classes, in order to create something like an employee, for example, you would create a struct for that employee. Anyway, that would be the memory segment, and you would be using something called var handles, which are references to the variables. Layout defines field order, size, and alignment, just like you do in C. Memory safe, endian aware, right? Big endian, little endian, so it takes care of that for you, so you don't have to think about it. And it's portable, okay? So once you write that in Java, it'll handle any underlying case, okay? So let's see how a struct is done here. So here we go. Maybe. So what I have on this one, anyway, let me start with the C kata that I have over here, and here's the C. Again, what I wanted to do here is just keep things really, really, really simple, so that way you can get it. So here it is. I have a struct here, which is going to be a point with X and Y, and this would be the type definition for point. And I'm going to do an instance squared. I will have a pointer to point, okay? And once I have this here, I will take point, dereference its X, point, dereference its X, et cetera, right? And all I'm going to do is do a distance squared from this particular point, okay? Again, I just compiled this. I got a dy lib or lib from it, okay? That's what I get. And let's come back over here to the kata. And here we go. All right, so here's distance squared. Let's see what's coming up on this particular one. This one has a memory layout. So what this one is just describing what the struct is, okay? And we have a struct called the point layout, or I'm calling it the point layout. And I have Java int with a name of X, because that's the name that we have inside of the struct. We have this one here, which is Y, okay? Again, that's just going to reference the X and Y that I have in there. Now here's an allocation for point layout. So off heap, it's going to set up a struct, okay? And here it is. And what I'm going to do is set at index, which means set X, set Y on that point. And again, all this is done on off heap memory. Now we just go about doing things the same way. The only thing that was different here was how we are establishing a struct, okay? But right over here, what we have is we have the down call handle. We'll use that linker, the lookup, and with the find, distance squared. And again, you'll have the structure that's associated with it. And let's go ahead and make a run on this one. And this is actually working on my machine, right? That's just the library that I'm using, and I'm building a bridge over to C, okay? Pretty cool. So let's continue. Pretty cool stuff. Let's continue with pointers, okay? So in foreign function memory interface, API, C pointers are modeled as memory segment values. So what I'm going to describe here is how do you send pointers to the methods. So T star pointer to something, and we're going to call a native function. So when we do that, we're going to allocate a memory using arena, and then use that memory segment to hold, and then pass that reference over to the method, okay? So let's take a look at this one. All right, here we go. On this one now, let's take a look at the C code for this one. And what we have here is we have copy string. Now for this one, I'm just going to call strn copy anyway, which is the standard C library for copying a string. But what I have here is I have a pointer to a character, which is going to be the source. I don't know why that didn't work. There we go. And I have a pointer for the destination, and I have a max length for that. And I wish to call this. So I have to deal with pointers on this one. How do we go about it? That was weird. All right, so hopefully everything still works there. Yep, there it is. All right, so let's come in over here And again, once you have that particular library, you should be good to go. So here it is. You just set up memory. Allocate from. This one is your destination, so I'm not expecting anything really big, so I can allocate a size of memory there. So I have a source and destination. What am I going to do here? Here it is. Except this time, one of the things that we are doing here is we are using this, which is called a value layout for an address, okay? So what we have here is we have address, and we have int. And if you're thinking, hey, that's the return type, it is not because this is of a type void, okay? So there's no return type. This will take two addresses, one for the source, one for the destination that will be filled, and the max size for that, okay? So I will go ahead and invoke that just like it was available in Java, and I should get that back, okay? Because all I'm doing for this one is I'm getting the string in return from the destination part of my foreign memory, okay, my off-heap memory. Is everyone good? I think one of the things, like if I'm making it boring, that's a good thing, right? Because that just shows how easy it is. Like all this, you've got it, right? That's the best part about all this. Okay, very cool. Yeah. Right. The combined will go ahead and do that for me. Yep. So yeah, you don't have to worry about it. In the U.S., kind of an interesting thing though is like we have. I don't know if you saw that. Like previous president had made a declaration to have like memory safe programs, and that company should be using that. And the C folks were like, right, and have garbage collection and things like that. So, but yeah, that's what this is able to do. Yeah, please. Like from Java, or
How could I accomplish something on that?
I think, yeah, let's wait for JExtract because I think JExtract will do that for you. So it can take the header file and create whatever it is you need. And then from there, I think you could just call a struct from there because that's just going to be already pre-made for you, and you're just able to make that reference on there. But I think that's probably going to be your answer on that. Yeah. Cool. So receiving pointers. So native functions may return a pointer like, car pointer or void pointer or T pointer, or whatever pointer. So foreign function memory returns return pointers also as a memory segment. But here's where the twist comes in. The return segments, now it gets a little hard, we're just tuning it up a bit. Return segments have a byte size of 0. And they are opaque handles is how they call it. And the reason for this is because at that particular moment, they don't know what the size is or, what memory is available at that particular time. So you could run it, but what you have to do is you have to make a call to something called reinterpret. So that way you can gain access to that memory that they point to. A little bit different there and a little bit of a complexity here. So let's take a look at that one. So what I'm going to do on this one is I'm going to call greet. What is greet? Greet is this one right over here. So right over here is greet somewhere. Where's greet? Oh, down here. Yep. Okay. So in this one here, just let's make this one very simple. That one's returning a pointer to a car. So if I come back over here, that's what I'm calling, okay? And here's the function descriptor of, and it's not asking for anything, it's just going to return an address to me. And that's what this represents. So I'm going to call invoke here, greet invoke, and this will be a memory segment. And I know it will be a memory segment because that's a pointer. Now, what we're going to do over here, though, is that when this is called, come in over here. When this is called, we're going to take a look at the byte size and show that this is going to be a 0-length byte that we get in return. Then what we're going to do here is we're going to have this reinterpret here, which is going to provide a particular size to it. This will be a memory segment here, which would be the thing that will be readable for that. Then what we're going to see here is what's the size here. So this one over here is going to come out to be size 0, and this one over here is going to come out to be whatever the size that we destined over here. And then what we will do is we will go ahead and grab that particular result. So let me go ahead and run that one. And again, just because we are returning a particular reference, here it is. And we could tell right over here on the read here that the first time, I end up calling it malloc, but the first time I called invoke, it's not called malloc, that I got a 0 size from that. But after the reinterpret, I did get 100 from that. And as far as the code goes, what we should see here is that we should see hello from C. Okay? Cool.
Yeah. Did it copy means another copy in area memory, or did it directly just take it?
That's a good question. You know what? I'm going to go to the, it returns I think it does create a new one. Let's take a look here. My official answer is, I don't know. Returns a new memory segment that has the same address and scope as this segment, but with a provided size. So I think that's what it does. Creates that memory segment, fills that up, and then returns that. Yeah, excellent question, which I didn't know, but that seems to be the answer. Yep.
What happens if I allocate
If you allocate some memory and the return size is what?
because at the end, that I my
I think this thing's keeping me. Say it again a little bit louder, please.
we have reading the memory
Yeah, right. Mm-hmm.
that if I suppose you give it say 1 byte, okay, reinterpreting and reading, but I think that the text of the byte that is being returned is a bigger.
Ooh, that's a good one. I don't know. There's another I don't know, but I think that's easy to find out, right? Because I could just give it a size of 1, and we'll see what happens. Is gambling allowed here?
Right.
All right, let's take a look here. So let's bring it down to 1 in here after calling reinterpret. I'm going to bet an exception on that one. I don't know. Yep, index out of bounds exception. There it is. So because that wasn't able to fit on the Java side, I knew that. No, I'm just kidding. I didn't know that. But thanks for that question there. So Java's going to be the defender essentially on here that, hey, what you're trying to do here is not a good thing, and we're going to prevent you from doing it. That's an excellent question. I learned something from that, so very much appreciate it. Okay. I should change that because next time I do this presentation, I'll be like, what the heck happened? And I'm not going to see it. So I don't know where I changed that. Yeah, right over here. All right, excellent. That was a good question. All right, so very cool. Now callbacks, this is where we're going to do the up call. Because what I want to do is I want to provide a stub on this one. So FFM provides passing up calls to C function pointers. So link up call stub and to convert a Java to a C function pointer. And we could pass that stub to a native method as a memory segment. Okay? So before we go into the restricted, let's go ahead and take a look at this one. So on this one, here's that callback. Okay? We have a type definition for something called a callback. And here's the callback here. Okay? And we have a int value. So whatever value that we're plugging in here, that's going to be called into that callback. Again, that callback is going to be something that has this type signature in here. And when we take a look at the Java side, and here it is, here we go. Here's the callback. All right, let's take a look at this one. A little bit more involved on this. And what we have here is the following. Function descriptor. Is someone get the door? Thanks. So function descriptor, Java int. And what we're going to do here is we're going to create a callback. This time it's a method handle, but not a method handle to the C layer. This one's going to be a method handle to Java. And what we have here is we have a find static. And I'm going to say, look inside of this class here, look for this method here, and here's the method type or the structure of that particular method. And that has a int.class and an int.class, and that's what this callback is. Where this one's going to be the return type, and this one's going to be the parameter that we are using. And here's that callback here, okay? So very much like a Lambda, we are sending that through to the C layer, and the C layer is going to call that back up. Does that sound crazy? Or I'm like, all right, okay, we're going to do this and this and this, and we're going to wire this up. And so, but that's what we're going to be doing. We're going to send that essentially a Lambda over to it, and then from there we're able, or the C is going to be able to call it back. So here's the apply callback with the function descriptor for this. This will be returning a Java int. This will be receiving the callback, and this will have the Java int associated with it. Let me go ahead and run that. And here we go. Okay. So green bar on here. We sent in a 7. C was going to, oh no, C was not going to multiply it by 10. We were in a long redirected sort of way, right? Because the stub here was x of 10. So let me wrap up what we just did. I'll use Andres here. I gave Andres a function, x times 10, given an x, and I gave it a 7. So I just said, here, you put it together. And that's what happened. Had that function, had that 7, and was placed together. The C did that, and all I got in return was, the assembled part, essentially. Okay? That's what that did. Pretty cool, right? And works pretty nicely. Yes?
Yeah.
It's there, like, what's a good use case? I don't know. I know it's there, and I wanted to talk about it. Let's see. Trying to think of one on the spot here. I guess, you know what? I'm going to defer to kind of like the way that we do, functional programming, because we need to create functions, all the time, and we have a special need as to what it is that we want to do. Maybe we want to run a particular sort, and we have a sorting algorithm, so it's some sort of function that we want to define. I could see a good reason there to where I want to do the callback in Java because, there's a Lambda or there's a procedure or I'll use the word verb. There's an action that we want to do that I just want to plug into C, okay? Kind of like the way we do reduce, like if you ever done reduce in Java, you get a seed, but you also put in a Lambda because you have the behavior. And you know what? I'm going to go even a little bit further here. The strategy pattern. So that's essentially what this is. If you're going to be making a call to C and you have a particular strategy that you wish to plug into C because it's not defined within your C layer, you're sending that function in because you have a certain way that you want that C function to behave. Yeah. Thanks for that question. That was a good challenge there. Nice. All right. Cool. I'm getting pictures taken when I'm all sweaty. What is my shirt looking like? Not too bad. This one's the warm read. All right. Cool. Any other questions? All right. So very cool and excellent questions here. So restricted methods. So you saw on the beautiful. You saw that when I ran these, it said down there -- enable, right? And it says you're going to have to put that in there. That's because we're using a restricted method. Some of these are going to be labeled as a restricted method. And so Java's just saying, look, just tell us you know what you're doing, is what that is. So restricted methods break memory safety, crash the JVM, circumvent any kind of boundaries. Here's this JAP here. And I found this one Pretty interesting. This is JEP 472, prepare to restrict the use of JNI. I think it needs to be changed. I think the title needs to be changed. And if you see here, I kind of clipped it, but you kind of see it down there. Summary, issue warnings about uses of the Java native interface and adjust the foreign function memory API to issue warnings in a consistent manner. Okay? And inevitably, it's going to be something to where you definitely want to restrict. I got it. Yep. So that's what this is. It's for both actually JNI and FFM, which is not necessarily, I don't know if it's true on like the restrict, but to where you're going to have to state, yes, I know, and I know I'm using restricted methods. I know I'm calling, native methods. So that's where that will come in. Okay. So finally here, JExtract, or two double finallys here. I have 10 minutes. I think I could pull it off. JExtract, what is that? This is cool. JExtract is, you download this from jdkjava.net. It is an application that you bring. And so what this will do, remember, you have a schema. I called it a schema. What is the structure of the method that you wish to call? That's a lot of work. So can you say, I want to go to each file, which has the signatures of the method, and generate this stuff for, I was gonna cuss. Generate the stuff for me because I don't want to do it. And that's what JExtract is going to be doing. So with this tool, you don't need to create down call or up call handles for functions because everything has already been done for you and it generates the code for you. You download this from this particular URL. Okay. So here's how it runs. So you have the include directory. Where do you find the H files? Output, where do you want to output this to? JExtract is going to create Java files for you. Target package. So where do you want to put this, right? I think a lot of demos will do com.unix, but you can decide whatever it is that you want. And so this would be the target package. What's going to happen though is it's going to create another package within there. So in this case, like org JExtract mylib dot generated is what it's going to be creating. Where the library is and the H file over here. Oh, this is where the includes are. Sorry, I got that part wrong. But here's where the H file is, and go ahead and create that for me. Okay? So let's run JExtract, and we'll see what this looks like. So here's the JExtract. A little funky though. Well, let's take a look here. So here's JExtract. Output, I want to output this to source main Java. The library is this FFM kata, which is referring to this one right over here. Okay. Now, you'll notice something here. My library is actually called lib ffm underscore kata dylib. But this one's called ffm kata. Okay. So you give it a name without the lib in the front or the extension dylib. So, oh, you know what? I was wrong here because I did put it under generated. I did that. I thought that was automatic. So right over here is going to be the package to where it goes. And here's where the include library is. This one has to be an absolute path. So that way it could find that. And then the H file that I want to bring in. Here, I'll just run it just for fun. So I went ahead and ran that, and I think it completed. And what it generated is the following, and here it is. And I'll just show this one. All that junk, and this is just my tiny little kata in here, but all that stuff is in here. Let's take a look. Let's see, where add-ins. Yeah, here it is. Here it is, right? Whatever the segment is, whatever the address is, whatever the down call handle is, all that stuff has automatically been generated for me. And that's really cool. Because what I could do then is the way that I can call it is I'm running the same katas in here. And here it is. Look at that. Now, one of the things that you would need to do if you're going to be using this is you're going to have to state here where the library path is located. That's going to be the thing, because just because you used a .h file on this, that doesn't mean it's actually going to be loading the library for you. And you're going to have to state this. You could either do this as, a static, which probably isn't the best way to go about it, or you can do -d whenever you run your application, java.library.path, and just state where the library is going to be located, because at runtime, it needs to know where your libraries are. So that way you can use it. But of all the demos that I ran, here's what they are. Add ints, multiply double, right? And look at this one, right? I think this is probably leaning towards the question that you had asked about doing the point, getting it from the H file, stipulating the memory segment. And here it is. I want to do 3 and 4, and I want to call distance squared. It makes it even a lot cleaner, right? So that's pretty cool. So here's this one, the greet extracted. And if I run all these tests should run. Okay? And that's excellent. All right. I have 4 minutes left. This one I really, really wanted to do, which is I just wanted to see like a different language and if that was going to work. So what I have over here is, let's go over here to projects. So I have this project here if you want to try this yourself for the code. Again, my intent here was to make things in a kata very small so that way you can run this. And I love this. I think this is great. So here's Rust Math. Anybody use Nix? I think I talked about it in another session. I don't know if you were in that session. Ooh, nice. Thank you. That's a positive, I don't know what that was. That sounded like a little bird. Anyway, so right over here, here's Nix. I think Nix is cool. How many of you use Brew and have a Mac or Choco or any kind of package manager like that? This one, imagine if you had a package manager and it was local. So like for your particular application, like this right here for this particular application, I just want Rust C, Cargo, Rust format, and Clippy. But only for this application, right? And that's what that is, okay? I'll just give a quick shout out here to Nix, because check this one out. Let's say I want to use Rust C. I don't have Rust C, but if I do Nix shell right in here it is, or not. Let's see. Oh, I'm in the wrong place. Projects, and let's go over to Rust Math here, and there we go. Now let's do Nix shell, because I think it was in here. Nope. Where was it? Oh, it hits right in here. Nix shell. There we go. I was in the wrong folder. So as I'm running this here, there we go. Notice the prompt had changed here. And if I do Rust C, it's here. Okay. But once I exit off of that, then it's gone. Right. And I love that because every project has its own. Anyway, so what I did here is I ended up running this Rust Math here. And here's the Rust here. This shows an example here. This has an extern, so that way it could externalize a C call in here. Rust has something that's called no mangle. And so if you want to do this and build a bridge from Java to other programming languages, you're just going to have to read up on some of these particulars in here. Every language has its own way to externalize C, so that way you can attach to it. And it just so happens that Rust has its own, right? And so it has this no mangle here to make sure that the function that we get out of here is actually a square. I love Rust. That's what Rust looks like. And am I able to, so given this then, when I create this Rust here, so Rust uses something called Cargo. It's kind of like their Maven. I don't know if they like that or not. But right over here, we have librust math dy lib, okay? There's the library there. And I could just call it just like anything else. So my final part, my final coup de grace over here is, let's run this as a Rust, okay? And there it is, okay? I have a library lookup. I'm resolving the Rust path over here as to where that's located. And here's the library. And I'm just going to run this square function. And from Java, I am running REST. Okay? So pretty cool. All right. Hope you got a lot out of it. Oh, look at that. I hit the nail on the head on that one. So we're up with time, but I'll be around for any questions. And thank you very much, everyone.